Well, I guess it's good afternoon now. Anyway, I will try to make it fast. I didn't realize I was only going to have about 10 minutes to talk, 10, 15 minutes to talk, but a lot of the stuff you've already seen, and I'll touch on some other factors. I'm going to give a outline, introduction, project scope, talk about durability issues. So this will be tied into the talks before the ones that were occurring right before the last one, other than for freeze thaw. And we'll look at corrosion and crack related testing and give some conclusions. This is part of an FHWA BA exploring the use of novel alternative cementitious materials. And other people on the team, I'm not going to read their names because some of them I have a hard time pronouncing them, so I'll just let you take a look at my colleagues at other places that I worked with, and a few of them have actually spoken here today. But that was a pretty nice team, great group of people to work with. I think we know what these are by now, so I can probably go through this side. But the whole idea of what we were trying to do is actually try to use this stuff in highway applications, not for patching, but for actually replacing large amounts of concrete. So we had guidance how we're going to go. We'll look at them and chemistry, a lot of information probably shown this morning when I was at a committee meeting, didn't see, and the various other places we get to the place of where we want to be. So we had durability issues. Some of them were just one matter of fact was just addressed, freezing and thawing, salt scaling, dimensional stability. We looked at chloride ingress, corrosion reinforcing bars, and the effect of cracking on that, sulfate resistance, and ASR. I'm only going to talk about the ones in bold. Okay, so basically the ones more related to corrosion. All the concretes in the study were produced at water to cement ratio 0.41, except A1, which required a lower amount. And we measured transport properties from the chloride, and we also measured them after corrosion testing. So we actually measured the chloride contents in the concrete in the actual concrete that was under corrosion testing. I think we also did some comparisons, which we had some of our mortar samples where we had actual point count. We actually did normal titrations, and they compared extremely well with the micro X-ray experiments at Oklahoma State. Looking at the controls, now this is 1556, the standard method. You pound them for 28 days. We also did longer times, which I'll show you. But for the control, the OPC, nice diffusion curves, and about a value of about 4 times 10 to the minus 12 meters squared per second. We have a CAC2, which I believe, which also did extremely well on this, a little bit higher than the control, but also had a little than OPC, but once again, very nice curves. Looking at from CSA1 that we had a higher diffusion coefficient. We're not doing anything artificial here. This is just taking the material that's been cured in a fog room, so it's nothing to leach out, and they're put into this salt water on top of them. So I mean, this is what it's going to see in the real environment. We're not guessing on what type of pour water to put around there or anything else. But once again, fairly nice curves at this point. And we started to look at what's going on here a little bit. So we looked at how much the chloride was water soluble and how much of it was not from the acid soluble range. And we can see that the OPC at very low, at the relatively low chloride contents, most of the chloride is bound. And as you go farther out, if you go out to a very high chloride content, there's the higher values at the right-hand side. At that point, you absorbed all the chloride that you can on the cementitious phases, so most of it's now going to be in the pore water solution. And you can see that the CSA and the samples were a little bit lower, the blue lines on the bottom. They do not bind as much chloride as are bound by the other phases. It's probably because there's no C3A in that, which is known to be combining with chlorides. So that's an important feature. We also looked at NT build. That gave us some funny results at various. But on the left side we have 1556, and we can see we looked at 2 ages, and we can see at one of the CSA2s went up in time, but, but everything else is coming down in time that you'd expect. We go over to another NT build test. The one that was going up came down a little bit, and others are pretty much, and there was one other one that, another CSA one went up instead of down. So it's hard to know what exactly is going on, but we did measure these things out farther out in time because they get rid of some of the early day changes. And in general, we looked at bulk diffusion versus bulk conductivity. When we ran the bulk conductivity, that was on samples that were just cured in a fog room, no lime water on them, no assimilated pore water, and I think we're kidding ourselves if we think we can get exactly what the assimilated pore water is for everything we're looking at. But we did the bulk diffusion versus the bulk conductivity, all these things, bulk conductivity, bulk diffusion versus the bulk conductivity, we can see that in general, when the fusion drops, the conductivity drops also. What should be noted here, and I think it's kind of alluded to by some of the previous speakers, that the same conductivity and the same bulk diffusion don't necessarily agree. A different material will have a different relationship. That, of course, would be related to the formation factors and some other things. So you can see down the road, you got a couple things that have the same, let's say 2 times 10 to the minus 12 on the bottom, but there's a fair range of where the conductivities are. So for a given material, you can get the conductivity relationship to the bulk diffusion, but it's not the same conductivity relationship, isn't the same bulk diffusion for any other material. And the same thing if we did NT build with conductivity, same general idea. The NT build numbers go up, and when the conductivity goes up, but once again, for a given material, the conductivity and the bulk diffusion as a more known relationship. And so we should keep that in mind. And we just looked at realizing that bulk conductivity is in general related to the diffusion coefficient. We just measure that over time. And you can see in general all the materials we tested, most of them came down in time. One of the CSA stayed kind of low there, but it's bouncing around, but all coming down. The only one that actually went up in our materials was the CAC, which was a calcium aluminate cement, and somewhere around, we always saw it on corrosion tests and everything else, around 90 days or so, it went through a phase transformation as far as we can say, and the values changed. So you can see, but in general though, long term, and you can see this after 1,000 days, so we're looking at 3 years worth of data here. We also looked at the ratio of the bulk surface resistivity to the bulk resistivity to the conductivity, the surface conductivity. And in general, when the ratio, a decrease in the ratio implies that the outside is becoming, is becoming more permeable than the inside. And we see that for the CSA, for the CSA 3 sample, which was the pure calcium aluminate, it was actually deteriorating on the outside where the water was coming in from in the fog room, only in fog room exposure for these. So for the corrosion testing, we had a whole various list of things. We looked at both concrete, cracked, and fatigue beams. We also did some testing in mortars. The mortar testing was a simple test where we had a small bar on the top, a larger bar on the bottom, and we pounded them with chlorides. These samples were never stuck in lime water. They're all fog room cured, so they're not affecting anything in there. And we ran those tests for a various period of time, and we looked to see, we moved them when we had corrosion occurring in OPC. In this particular series, did not do necessarily as well as some of the other things, but A1 did well. So we have some of, basically what we have is, we have a number as to, the blue number is how many we pulled out, and this is what cycle. So 5 cycles, we pulled out 3, I think that's it. Oh, there's the cycles, 5 cycles, we pulled out 2 of them, and going along the line. There was 10 of each, but we'll get more back into this a little later. With the cracked beams, these were large beams, 30, basically 6 by 6 by 22 or so inches, and we can see that we measured the macrocell corrosion occurring on these, and CACT, which was calcium aluminate with a B-light in it, did extremely well, as did some of the, a couple of the CSAs, where one of the CSAs was down there with the polymer was down there. And other ones eventually went into corrosion at one time. The CAC, which started off pretty low, just took off when it went through its phase transition. Once again, these things aren't seen in any environment other than chloride, the normal environments they would be expected to see. Looking at corrosion potentials in time, they very much show the same effects, with the control samples starting to passivate a little bit. But, you know, even though I'm an electrochemist, I do like to look at my bars when I'm done testing, because I think, you know, if people tell me I didn't see any corrosion, well, that particular test method only is measuring the macrocell. It's not measuring what's going on locally on the samples. So you can see on the control sample, there's corrosion on the top, but the bottom bars are pretty clean. The CAC2, which was aluminate, you see you got a fair amount of corrosion on the bottom bar as well as the top bar, indicating that that's going to take away from your macrocell. If you have a bottom bar corroding, it doesn't send any cathode current up to the top bar. And we have the same thing occurring on AA1 to a little less extent, some corrosion on the bottom bars. And the CAC2, with a much longer time than everything else on here, because they were the very last things to fail. They had a little bit of corrosion on the top, CAC-T on the top bar, and very little on the bottom bar. So the basic at OPC and the testing OPC and CAC-T were the only ones that did not have corrosion on the bottom bars. There shouldn't be much chloride on the bottom bars. And here's looking at CSA1, and we got CSA2, and you got corrosion. Even though they had lower macrocell currents, they had corroding bottom bars in some cases, pretty bad. So once again, there's no, on these particular, some of these cases, there's no chloride down there, so the bars shouldn't be corroding. Some more autopsies. The polymer version that we had did much, much better, but it still had some little specks of corrosion, and some on the bottom bars again, and the same thing, minor corrosion on bottom bars, away from the cracks, away from the cracks. So overall corrosion results is that we found out that the calcium aluminate cement with B-light in it did very well corrosion-wise. The CSA2P had very good macrocell corrosion performance. Still some corrosion on and the corrosion on the bottom bars do offset macrocell performance. OPC had corrosion on the top bar, but no corrosion on the bottom bars. And the other ones had a combination of both. And once again, on the testing there. So let's see. Looking at the types of, you get an idea what the type, how we cracked it. These samples were cracked in flexure. Oh, real quick, so you can see here's we put a we saw the hole, and then we put them in flexure. You can see the cracks forming. And I guess you'll just have to look at the paper on the, on the website to see more of it. The interesting thing is the CSA2 appeared to actually seal the crack a little bit over time, which was interesting phenomena. And there's our calcium aluminate cement. You can see how that one compared to the other ones is just falling apart. Synopsis of the, so anyway, that shows kind of synopsis of the cracking, basically usually through the aggregates and sometimes around the aggregates, and the CAC was only cracking around the aggregates, showing deterioration. We measured chloride profiles after testing, and of this, and you can see we got about, at the crack, we get about for OPC and the CAC-T, we got an increase of about 10 times in the diffusion coefficient at the crack. For the CSA1 and CSA2s that we tested, there's orders of magnitude difference at the crack versus that. Not a whole lot of chloride in there because there's no binding, but it's all the way, I mean, it's not doing anything to stop the stuff from coming in the crack as far as diffusion. And the same thing on this one. We look at chloride distribution far and away from the crack. You can see that in general, the OPC had a fair amount at the crack, as you expect. All of them had a fair amount at the crack, but you can see that away from the crack, some of them were very low away from the crack, some were not. And you can see at the bottom of the crack, some of them actually had a fair amount of corrosion. Chloride got into the bottom of the cracks too. Lower chlorides into the CSA2s than the other ones, and the A1s, but also due to less binding. So bulk pseudo-diffusion coefficients compared to OPC, higher for CSA1 and CSA2, approximately the same for those two. Chloride is surfaces subsequently in the interior is less for the ACMs. It could be due to reduced chloride bonding found in the mixes and all cracks except for CA. So no, except for CAC2, cracks with no effective depth or crack, whereas there was a decrease in chloride depth of crack in OPC. Equivalent corrosion rates at lower chloride levels except for CAC2. And let's see, I can go ahead, more decrease in iron penetration over OPC. And basically the corrosion occurring in CSA specimens occurred at a reduced chloride levels, consistent with low chloride binding, and a lowering of pH or more soluble sulfate could be potentially present, contributing to this. The polymer did help to reduce the overall corrosion and aggressive chlorides. And thank you.